The sky over eastern Iowa on the morning of August 10th, 2020, looked almost boring. A few scattered thunderstorms had rolled off the plains of South Dakota overnight, nothing that made the local news, nothing that made anyone cancel a barbecue. By midday, a wind gauge outside Cedar Rapids recorded gusts of 140 miles per hour, roughly 225 kilometers per hour. Wind speed equivalent to a major hurricane, arriving over a landlocked city 1,100 kilometers, about 700 miles, from the nearest ocean. There was no eye. There was no spiral visible from space. There was no name assigned by any hurricane center, because storms like this one don't get names. They get a word most Americans had never heard before that afternoon: derecho. Meteorologists watching the radar that morning saw something that should have taken days to build take less than an hour to become one of the most destructive wind events in American history. And by nightfall, it had cut a scar of wreckage from South Dakota to Ohio. What happened inside that storm, the invisible engine that let a thunderstorm outrun a hurricane, and the reason forecasters and the public alike keep underestimating it, is exactly what we're about to take apart, piece by piece, including the part almost nobody outside meteorology circles has ever had explained to them: why the warning system built to catch this storm is, by its own design, always a little bit late. Before we go further, if disasters that hide inside ordinary weather are your kind of story, this is the channel for that. We take real data, real events, and the actual physics behind them, and we build the full picture nobody hands you in a 30-second clip. Subscribe, because the next derecho is already forming somewhere in the atmospheric data right now. And when it arrives, we'll be tracking the same signals the scientists are. Tell me where in the world you're watching from, and whether a straight-line windstorm like this one has ever touched your part of the map. Now, let's get into it. Every meteorologist learns to read a radar screen the way a cardiologist learns to read a heartbeat. Most severe weather has a signature, a shape you can recognize before the storm ever arrives at a town. The most famous one is the hook, a small, curling comma at the back edge of a supercell thunderstorm, the radar's way of drawing a tornado's rotation before the tornado ever touches ground. Meteorologists have hunted for that hook shape since Doppler radar became widely available, because it means one thing and one thing only: rotation. Concentrated, violent, and narrow. But on the morning of August 10th, 2020, the shape crawling across radar screens over South Dakota and Nebraska wasn't a hook. It was a bow, a long, gently curved arc of thunderstorms, bulging forward in the middle like a drawn bowstring about to release an arrow. A bow echo is the characteristic radar return from a mesoscale convective system that is shaped like an archer's bow. The first time a forecaster sees that curve appear and sharpen on a loop of radar frames, the reaction isn't relief that a tornado warning won't be needed. It's the opposite. A bow echo means the storm has stopped behaving like ordinary thunderstorms and started behaving like a single machine. Here's the physical picture worth holding on to, because it explains almost everything that follows. Picture a bedsheet hung on a clothesline in a stiff wind. Along most of its length, the sheet flaps and ripples unevenly. But if the wind finds one weak point in the middle, the sheet doesn't just ripple there, it balloons outward, faster and farther than the rest of the sheet, dragging the ends along behind it. That bulge, racing ahead of the flanks on either side, is exactly what a bow echo is on radar. The middle of a line of thunderstorms outrunning its own edges because something inside that middle section is accelerating harder than anything nearby. What's actually happening up there, invisible to anyone on the ground, is a colder, denser pocket of air, plunging down out of the storm faster than the rest of the line can match, punching the center of the system forward like a fist through cloth. The analogy holds up to a point. A bedsheet doesn't have a name for the exact air current doing the pushing. Meteorologists do. They call it a rear-inflow jet, a river of air drawn into the back of the storm system and shot forward at altitude before crashing down to the surface. And we'll get into exactly how that engine assembles itself soon, because it is the single most important mechanical detail in this entire story. The term itself is younger than you might expect for something this dangerous. The term bow echo was first used by Theodore Fujita in his May 1978 paper, Manual of Downburst Identification for Project Nimrod. Fujita, the same scientist who later built the tornado intensity scale still used today, was staring at radar returns from a killer windstorm in Wisconsin and realized meteorology didn't yet have language for what he was looking at. That gap in vocabulary is not a small detail. It tells you something uncomfortable. An entire category of storm capable of hurricane-force destruction was moving across the American interior for decades before anyone had officially agreed on what to call its radar signature, let alone built public warning systems specifically shaped around it. And here's the part that should stop you. That gap in vocabulary never fully closed. Even now, in the summer of 2026, there is still no derecho warning issued by the National Weather Service. There is only a severe thunderstorm warning, the same one used for a garden variety storm that knocks over a few lawn chairs. The bow was named. The threat behind it never got its own alarm. So what was crawling across those South Dakota radar screens that August morning wasn't unprecedented in kind. Bow echoes happen dozens of times every warm season across North America. What was unprecedented was scale and speed, and how quickly the bow sharpened into something that met a much stricter definition, one reserved for only the most extreme events of this type. That distinction between an ordinary bow echo and a true derecho is where this story turns from an odd radar curiosity into a genuine wide-scale disaster. And to understand why, we need to step back from the radar screen entirely and ask a more basic question. If this storm produces wind as strong as a hurricane, wind capable of flattening a forest and stripping a city's tree canopy in under an hour, why doesn't it look anything like one? Why does something with hurricane-force winds have no spiral, no center, no eye at all? That absence is not a minor technicality. It is the whole reason this storm type gets misjudged, underestimated, and underprepared for, year after year, region after region. And the answer to why starts with understanding what a hurricane actually is, mechanically, underneath all the satellite imagery we're used to seeing. A hurricane is, at its core, a heat engine built around rotation. Warm ocean water evaporates. That water vapor rises and condenses, releasing heat that makes the air rise faster, and the whole system spins tighter around a low-pressure center, the way water spirals into a drain. Except the energy keeps pouring in from below, so instead of draining away, the spin intensifies and sustains itself for days. Think of a figure skater pulling her arms in during a spin. Angular momentum concentrates, and the rotation speeds up. A hurricane does something similar with wind, drawing air inward and upward around its own low-pressure core, faster and faster, until it has an eye, a place at the center where all that violence briefly goes still, because everything is being pulled toward the middle rather than pushed away from it. A derecho has none of that architecture, and here's where the metaphor has to change entirely, because the physics actually are different. If a hurricane is a skater pulling inward to spin faster, a derecho is closer to a bobsled accelerating down a chute, gravity and momentum doing the work, in a straight line, with no pulling inward mechanism at all. Instead of warm air rising and organizing into rotation, a derecho is driven by air doing almost the opposite. Cold, dense air, formed inside a thunderstorm's rain and hail, sinks hard and fast toward the ground, spreads outward when it hits the surface, and shoves everything ahead of it forward, like water pouring off a table. It all has to do with something called a downburst. When the wet air in a thunderstorm meets the drier air surrounding it, the water in the air evaporates. When water evaporates, it cools the air around it. Since the cool air is denser, it rapidly sinks to the ground and creates strong winds called downbursts. There's no center pulling this system together. There's no eye, because there's nothing here that spins. The wind moves the way water moves down a hallway when a door is thrown open, outward, forward, along whatever path offers the least resistance, all pointed the same direction. That, incidentally, is exactly where the storm's name comes from. The word derecho means straight ahead in Spanish. That word wasn't coined by a Spanish-speaking meteorologist watching a Caribbean storm. It came from a University of Iowa physics professor working almost a century and a half ago, wrestling with a very specific problem. Nobody had a name for a storm that did tornado-level damage without a tornado's telltale spin. The word derecho was coined by Dr. Gustavus Heinrichs, a physics professor at the University of Iowa, in a paper published in the American Meteorological Journal in 1888. Picture Heinrichs standing in a field of felled trees somewhere in the American Midwest, all of them pointed the same direction like fallen dominoes, and realizing that everyone around him was calling this tornado damage simply because no other word existed, even though nothing about the debris field showed the telltale rotational scatter that a tornado leaves behind. He needed the opposite of a word that meant to turn. In Spanish, tornado damage twists things in circles. Derecho damage drives them all one way, like a crowd fleeing through a single doorway. Heinrichs gave science that word in 1888. It then sat almost unused for nearly a century, resurfacing seriously in meteorological literature only in the 1980s, as researchers began systematically studying long-lived windstorms and realized Heinrichs had already solved their vocabulary problem 100 years earlier. What still lay ahead, though, was a numerical test far stricter than any dictionary definition, a threshold so demanding that most bow echoes never come close to it, and one a certain cluster of storms over South Dakota was, within decades, going to clear with room to spare. The bobsled analogy needs a caveat here, though, because a derecho isn't one single downburst sliding across a map. That would just be a strong, brief thunderstorm gust, over in minutes. What makes a derecho different, and genuinely rare, is that these downbursts don't fire once and die. They fire in families, one triggering the next. The cold outflow from one downburst helping to trigger and accelerate the next cell just ahead of it, for hour after hour, across hundreds of miles. A derecho, pronounced derecho, is a widespread, long-lived windstorm associated with thunderstorm squall lines and quasi-linear convective systems. A derecho is a bow echo, but not all bow echoes are derechos. The formal bar for earning that name is strict by design. A more recent, more physically based definition of derecho proposes that the term be reserved for use with convective systems that not only contain unique radar-observed features, such as bow echoes and mesovortices, but also for events that produce widespread damage over a great distance. As of the most recent revision, adopted in May of 2025, meteorologists require widespread wind gusts of at least 58 miles per hour, about 93 kilometers per hour, sustained across the storm's entire path, plus at least 3 separate gusts of 75 miles per hour or greater, that's about 120 kilometers per hour, wind strong enough to flatten a cornfield or peel a roof. Each of those violent gusts separated from the next by at least 80 miles, roughly 130 kilometers, so the storm can't sneak past the definition on the strength of one lucky downburst near its birth. That's the technical bar. In plain language, to be called a derecho, a storm has to behave like hurricane-force wind for hundreds of miles, without stopping, without an eye, without a name from any national hurricane center, and it has to do it fast enough that most of the people in its path get almost no meaningful warning before it arrives. And on the morning of August 10th, 2020, somewhere over the Badlands of South Dakota, a modest cluster of overnight thunderstorms was about to meet every single one of those criteria in a way that hadn't been matched in living memory across that stretch of the country. Let's be honest about where the danger really lives in a storm shaped like this, because it isn't in any single number on a wind gauge. It's in the mismatch between how the storm looks from a satellite, an unremarkable smear of cloud, nothing like the terrifying spiral of a hurricane approaching the Gulf Coast, and how it actually behaves once it's overhead. A hurricane gives coastal communities days of warning, evacuation orders, boarded windows, a name people can follow on a map for a week. A derecho gives you a darkening sky, maybe half an hour, and then it's already past you and moving on to the next county at highway speed. That gap between visible threat and actual threat is exactly what was about to close over Cedar Rapids, Iowa, a city that had absolutely no reason that morning to think anything unusual was coming its way. At midnight on August 10th, the Storm Prediction Center in Norman, Oklahoma nudged its overnight outlook up to what forecasters call a slight risk. the second lowest rung on a 5-step ladder used to communicate the odds of severe weather anywhere in the country that day. The risk level was elevated to a slight risk at midnight on August 10th, prior to the onset of the damaging storms. Slight risk sounds almost dismissive if you don't know the scale, and to most people checking a weather app before breakfast, it would have looked like nothing more than the promise of some afternoon thunder. Temperatures and dew points were between 70 to 80 degrees Fahrenheit, 21 to 27 degrees Celsius across the Midwestern U.S. around dawn on the morning of August 10th. That's warm, humid air, roughly 21 to 27 degrees Celsius of dew point, meaning the atmosphere was thick with moisture, the fuel any thunderstorm needs to burn hot. Winds blowing from the west were juxtaposed atop near-surface winds blowing from the southwest and south, resulting in strong wind shear over the region. That's the second ingredient, layers of wind blowing in different directions at different heights, which is exactly the kind of atmospheric tension that can organize scattered storms into something far more coherent and dangerous. The same way twisting a wet towel in opposite directions at each end builds tension that eventually snaps into violent motion. Nobody writing that midnight outlook yet knew exactly how fast those two ingredients were about to lock together, or that within 12 hours, the same office would be forced to upgrade this stretch of the map twice over, scrambling to keep pace with the storm that was already outrunning its own forecast. The storms themselves had unremarkable origins. The derecho began as a cluster of scattered thunderstorms that had formed during the previous night over south-central South Dakota. These storms tracked east along the South Dakota-Nebraska border and became better organized and coalesced, producing hail with diameters between 1 to 2 inches, 25 to 51 millimeters, and wind gusts between 60 to 70 miles per hour, 97 to 113 kilometers per hour, over a narrow swath. Hail the size of golf balls to ping-pong balls, wind gusts in the 60 to 70 mile per hour range. Serious for a normal thunderstorm, but nothing that screamed historic. Forecasters watching the radar loop that morning, though, could already see the shape of the line sharpening, the bow beginning to draw itself. By 8 in the morning, the Storm Prediction Center didn't wait for the usual scheduled update. In response to these developments, the SPC issued a special convective outlook at 8 a.m., highlighting a now enhanced risk of severe weather for areas in the storm's path, including Cedar Rapids, Iowa, the Quad Cities metropolitan area. That's an unscheduled bulletin, the meteorological equivalent of a doctor calling you back before your test results were due, because something in the numbers didn't look right and couldn't wait. The storm crossed into Iowa and kept intensifying, feeding on the same warm, moist air that had been sitting over the state for days. By late morning, it reached the Des Moines metro area, where 70 to 80 mile per hour winds ripped through the city, and just north of downtown, gusts pushed past 100 miles per hour, roughly 160 kilometers per hour, flattening buildings and stripping siding in neighborhoods that had woken up to nothing more than a slight risk label on a weather app. As the storms plowed through Des Moines, the 11 a.m. update from the Storm Prediction Center upgraded central and eastern Iowa to a level 4-5 severe weather risk. Think about what that jump means in plain terms. In roughly 11 hours, the official forecast for this stretch of Iowa had climbed from the second lowest risk category on the entire national scale to the second highest. And the storm causing that climb hadn't even reached its worst city yet. That city was still ahead, sitting quietly under a Monday morning sky, about to have the word derecho burned into its history. Cedar Rapids had survived disasters before. Longtime residents still measured hardship against the catastrophic flood of 2008, the kind of slow-building water disaster a city can watch coming for days and prepare against with sandbags and evacuation notices. Nothing about August 10th offered that kind of runway. The term derecho was unknown to most everyone in Cedar Rapids until August 10th, 2020, when we were faced with one head-on. The Midwest is known for flooding and tornadoes, but no one anticipated a fast-moving hurricane-like storm with straight-line winds of up to 140 miles per hour. The line raced east out of the Ames and Marshalltown corridor, following Highway 30 toward the city with almost no loss of strength, gathering rather than weakening as it went. Another area of 100+ miles per hour winds developed east of Ames and raced down US 30 into the Marshalltown area and eventually Cedar Rapids. When it arrived, it didn't arrive as a gust. It arrived as a wall that refused to pass. The worst damage occurred in the Cedar Rapids area, where winds between 120 to 140 miles per hour swept through, and the city experienced winds greater than 60 miles per hour for almost an hour. Say that back to yourself slowly, because it's the detail that separates this storm from almost every violent wind event most people have ever lived through. A tornado, even a devastating one, is typically on top of any single building for seconds, occasionally a couple of minutes. This was closer to an hour of sustained, severe, structure-threatening wind, with individual gusts touching Category 4 hurricane strength. Originating in eastern Nebraska and moving through Iowa and Illinois, the derecho formed suddenly on Monday, August 10, 2020, producing hurricane-force winds that reached up to 140 miles per hour for up to 40 minutes in some areas. 40 minutes, not a burst, not a squall. 40 minutes of wind, strong enough to be functionally indistinguishable, on paper, from a hurricane making direct landfall. Except this landfall happened over 1,000 kilometers from any coastline on a Monday morning, over grain elevators and elementary schools, and quiet residential streets that had never once needed to think about hurricane shutters. Nick Burgess, a Cedar Rapids area resident, was caught in it with his family. Iowan Nick Burgess remembers being caught off guard by the derecho that pummeled his home state on August 10, 2020, with hurricane-force winds, leaving billions of dollars in damage in its wake. His family had to leave their car behind and make their way home on foot, past fallen trees and downed power lines, arriving to find that 2 limbs from the maple tree in the yard had broken off and fell through their roof. What he remembered most afterward wasn't the noise. "I just remember that first night, it was so quiet," Burgess said. That silence is worth sitting with for a moment, because it tells you something about the scale of what had just happened. An entire city's worth of engines, air conditioners, televisions, streetlights, all gone dark and dead at once. The ordinary electrical hum of American life switched off across 74 square miles in under an hour. Because that is what the wind did to the city's backbone. Damage from the derecho reached all 74 square miles of Cedar Rapids, making it more devastating than the flood of 2008. Over 95% of the city lost power, and major roadways were impassable due to debris. Picture nearly every home, every business, every hospital corridor and grocery store freezer in an American city of well over 100,000 people going dark in the same afternoon. Not from a grid failure hundreds of miles away, but because the physical wires and poles carrying that power had been shredded, snapped, and dropped across yards and roads, block by block. The storm damaged power and communication lines and cell towers, making it hard to share information and resources in the immediate aftermath. The city responded by hand-delivering printed materials to stores and food sites. Think about that for a second. A modern American city, in the year 2020, reduced to distributing paper flyers by hand because cell towers had been knocked flat, the same way a 19th century town might have shared news before telephones existed. That is how completely this storm erased the layers of infrastructure people don't think about until they vanish all at once. The trees told the same story from a different angle. Cedar Rapids had long been proud of its canopy, mature oaks and maples lining streets that had stood through decades of Iowa winters. An estimated 670,000 trees were lost, 65% of the city's tree canopy. 65%. Not damaged, lost. 2 out of every 3 trees that had shaded those streets that morning were gone by evening, uprooted or snapped clean through by wind that, as we've already established, blew in one direction only, with none of a tornado's narrow, twisting fury to explain the scale of it. This was width, not focus. Devastation spread evenly across dozens of square miles, rather than concentrated along a quarter-mile-wide tornado track. and people died in it. It was the most expensive thunderstorm in U.S. history and killed 3 Iowans. Across the broader path of the storm, from South Dakota to Ohio, the toll climbed higher still. It covered 770 miles in 14 hours, leaving a trail of destruction, including 4 deaths in their wake. 4 deaths, and 3, depending on which stage of the storm's life is being counted. The discrepancy itself is a small, grim illustration of just how spread out and slow to fully tally this kind of disaster is, compared to the tight, well-mapped devastation of a tornado's track. The number that should genuinely unsettle you, though, isn't a wind speed, it's the shape of the devastation on a map. Officials in Cedar Rapids didn't compare this storm to a tornado outbreak or an ice storm. They compared it, directly, to their worst flood in living memory, and said this was worse. A city that had spent over a decade rebuilding its psychological relationship with disaster around slow-rising river water had just been shown, in less than an hour, that the sky itself could do more damage than the Cedar River ever had. And the wind that did it didn't even have a name recognized outside meteorology textbooks, didn't trigger an evacuation order, didn't get a category number broadcast on the evening news the way a hurricane would have. What we haven't touched yet is the machinery that let this happen at all, the exact chain of physical events, downburst after downburst, that let a cluster of ordinary morning thunderstorms over South Dakota grow into something that could sustain hurricane-force wind over hundreds of miles without ever losing its nerve. Because the truth is, once you understand the internal engine of a derecho, the rear-inflow jet accelerating at altitude, the cold pool spreading beneath it like water under a door, the exact geometry that turns a line of storms into a self-sustaining wind machine, you start to see why this kind of storm has a body count that quietly outpaces entire categories of tornado. Why the warning that reached Cedar Rapids that morning came only after the storm was already committed to its path, and why a stretch of the American interior gets hit by one of these, on average, almost every single year, whether the country is paying attention or not. That machinery starts small, and it starts almost boringly, which is part of why so few people ever see it coming. Every derecho begins as nothing more than an ordinary cluster of thunderstorms, the kind that forms on hundreds of summer afternoons across the middle of North America and produces nothing worse than a good rain and a rumble of thunder. The difference between that harmless cluster and the storm that put Cedar Rapids in the dark lies entirely in what happens inside the clouds once the rain starts falling. A chain reaction most people will never see because it unfolds several kilometers above their heads, invisible even to the storm chasers standing directly underneath it. Picture a thunderstorm as a tall glass of water, with ice cubes dropped in from above. As rain and hail form high inside a storm cloud, they drag air down with them, and that falling air cools rapidly as the precipitation evaporates into it. The same cooling effect you feel stepping out of a swimming pool into a breeze, water pulling heat out of the air around it. That cooled, heavier air doesn't drift down gently. It plunges, the way a bag of wet sand dropped from a rooftop falls faster than an empty one, and when it slams into the ground, it has nowhere left to go but sideways, spreading outward in every direction like water poured onto a flat table. Meteorologists call this spreading dome of cold, dense surface air a cold pool, and on radar and on the ground, its leading edge is what produces the sudden wall of wind a thunderstorm throws ahead of itself. The gust front that makes lawn chairs tumble and screen doors slam shut minutes before the rain even arrives. In an ordinary thunderstorm, that's essentially the whole story. The cold pool spreads, the storm eventually runs out of the warm, moist air it needs to keep feeding itself, and within an hour, it collapses under its own cooling exhaust, the way a campfire smothers itself in its own ash. A derecho refuses to die that way. And the reason lies in a second current of air that most people have never heard of, one that develops only when the atmosphere's layered winds are arranged just right. As the storm's cold pool spreads out along the ground, it can, under the right conditions, help draw a fast-moving stream of dry air in behind the storm at mid-levels of the atmosphere, several kilometers up, and accelerate that air forward, wrapping it down and around the backside of the system, like water curling behind a boat's wake. Meteorologists call this a rear-inflow jet, and it is, without exaggeration, the derecho's actual engine. Rather than the storm gradually losing power as its own cold air smothers it, that inflow jet punches fresh, fast-moving air down into the back of the system, reinforcing the very cold pool that would otherwise be killing the storm, and shoving it forward into new, warm, unstable air ahead. Air the storm hasn't touched yet, air still full of fuel. The bedsheet in the wind image from earlier becomes useful again here, but sharpened. If an ordinary line of storms is a sheet flapping unevenly on a clothesline, a derecho is that same sheet with someone standing behind it, physically shoving the center forward with both hands. That shove is the rear inflow jet. Every time it strengthens, the bow in the radar image sharpens, the leading edge accelerates, and the line of storms stops behaving like a loose cluster of separate cells and starts behaving like one continuous, self-feeding wind machine. A machine that can, under the right atmospheric conditions, sustain itself not for 20 minutes, but for the better part of a day, marching across state lines without ever losing its structure. The analogy breaks down at the fine mechanical level. Nobody is literally pushing anything, but the effect on the ground is close enough to be useful. A wall of wind that keeps getting reinforced from behind faster than it can dissipate in front. There is a formal name for the theoretical tug-of-war happening inside that system, developed by 3 atmospheric scientists in the late 1980s, studying exactly this kind of storm. A balance between the outward push of the cold pool at the surface and the layered wind shear in the atmosphere above it. When those two forces are close to balanced, the storm's updrafts stay upright and powerful, feeding the system for hours. When the cold pool overwhelms the shear, the storm tips over its own leading edge and weakens fast. Get that balance right over hundreds of miles of open country, with abundant heat and moisture waiting ahead of the storm the entire way, and you get exactly what crossed South Dakota, Nebraska, Iowa, and Illinois on August 10, 2020. A storm that kept its engine running almost start to finish, outrunning every expectation forecasters had for how long a single line of thunderstorms should physically be able to survive. That same survival is exactly what breaks the warning system built to catch it, and the reason has nothing to do with radar hardware, and everything to do with a design decision made decades before this storm was ever born. Here's the uncomfortable truth sitting underneath every derecho disaster in modern American history. The entire warning architecture used across the United States was built primarily around tornadoes, and a derecho breaks almost every assumption that architecture depends on. A tornado warning covers a small polygon, typically a few dozen square miles, issued because a specific rotating storm cell has been spotted on radar or confirmed by a trained spotter on the ground. And it usually gives residents somewhere between 10 and 20 minutes of lead time before the tornado itself arrives. That system works because tornadoes, for all their terror, are narrow and briefly lived. A warning covering a small area for a short window of time is a reasonably good match for the threat. A derecho is the opposite kind of problem, on every axis that matters. Its damaging winds can span a swath 60 miles wide, roughly 100 kilometers, arriving simultaneously across dozens of towns, rather than sweeping through one at a time along a thin track. And instead of blowing through in minutes, a single derecho can remain dangerous for 6, 8, sometimes over 12 hours, chewing through 5 or 6 states in a single push. And critically, there is still no dedicated warning product for it. When a derecho's leading edge approaches a town, the National Weather Service issues what's called a severe thunderstorm warning, the exact same alert used for a storm that might drop quarter-sized hail and gust to 60 miles per hour for 10 minutes. To the person receiving that alert on their phone, there is no language distinguishing "expect a brief, scary squall" from "expect sustained hurricane-force wind for the better part of an hour." The word itself, derecho, essentially never appears in a public warning at all. It lives almost exclusively in forecast discussions written for other meteorologists, technical documents most residents will never see and wouldn't think to look for. This isn't a failure of any individual forecaster. The meteorologists at the Storm Prediction Center in Norman, Oklahoma, and at local weather service offices across the storm's path genuinely did their jobs well on August 10th. Recall that unscheduled 8 a.m. bulletin, escalated risk categories climbing through the morning, warnings issued county by county as the bow echo approached each new community in turn. The problem is structural, not human. Warnings for this kind of storm can only be issued reliably 10 to 20 minutes ahead of the leading edge reaching any specific town, because that's roughly the outer limit of how precisely radar can predict exactly when and where a fast-moving line will arrive at a given spot. Compare that to a hurricane, where the National Hurricane Center can tell a coastal county days in advance that landfall is likely somewhere within a stretch of coastline. Enough time to board windows, stock supplies, evacuate if needed. A derecho gives you the meteorological equivalent of someone shouting a warning from the other end of a long hallway, just as the door at your end is already swinging open. There's a second, subtler reason these storms slip past public attention, and it has to do with how the risk gets communicated well before the storm ever forms a bow on radar. Recall that the Storm Prediction Center's overnight outlook for August 10th rated the risk as slight, the second tier on a 5-level scale running from marginal to slight to enhanced to moderate to high. Those categories exist for good meteorological reasons. They describe the statistical odds of severe weather occurring somewhere within a large region, not a guarantee of what will happen at any one address. But to an ordinary person glancing at a forecast app before heading to work, the word slight reads as reassurance, not warning. Nobody canceled a soccer practice or moved a car into a garage because of a category that sounds, on its face, like a promise that nothing much is coming. By the time the outlook was upgraded to enhanced, and then to that rare high-end level 4 out of 5 just before midday, the storm was already barreling across central Iowa at highway speed. And for many residents, the first real signal that anything unusual was happening arrived not from a phone alert at all, but from the sky itself, turning the wrong color at the wrong time of day. Radar itself carries its own blind spot here, one that meteorologists have wrestled with for decades. Doppler radar is extraordinarily good at detecting rotation, the hook echo that flags a tornado, because rotation shows up clearly as air moving toward the radar on one side of a signal and away from it on the other. Straight-line wind offers no such contrast. A derecho's most violent gusts often occur in what's called a bow echo's rear-inflow notch, a specific little dip in the radar reflectivity pattern that experienced meteorologists learn to recognize, but which produces nothing as visually dramatic or unambiguous as a hook. It is entirely possible for a stretch of extreme, structure-damaging wind to be underway at ground level, while the radar image, to an untrained eye, looks like nothing more than an ordinary line of storms rolling through. That gap between what the radar shows and what is actually happening underneath the clouds is precisely why so many derecho events, both before and after August 10, 2020, have caught entire towns without adequate shelter time. And it's a gap the country's warning system has, to this day, not fully closed. Which raises an obvious question, and an unsettling one. If this kind of storm is this hard to warn for, and this destructive when it arrives, how often does it actually happen? And is there a specific stretch of the country that should be watching the summer sky more nervously than everyone else? The answer to that question has a name, and it was given by two scientists working for the same agency that would issue that slight risk outlook more than 3 decades later. In 1987, Robert Johns and William Hurt, both working with the forecasting operation that would become today's Storm Prediction Center, published a landmark study cataloging decades of these storms across North America, mapping where they occurred most often and how they tended to move. What they found was a corridor, not a random scattering, a belt of terrain running roughly from the eastern Dakotas and Nebraska, across Iowa and Illinois, into Indiana and Ohio, where warm-season derechos cluster far more heavily than anywhere else on the continent. They gave that corridor an informal name that's stuck in meteorological circles ever since: Derecho Alley. It is not a coincidence that this corridor overlaps almost perfectly with what most of the world knows by an entirely different name, the Corn Belt. the flat, intensely farmed heartland that grows a huge share of the country's corn and soybeans. The same broad, unbroken plains that make this land ideal for industrial agriculture also make it close to ideal for feeding a derecho's engine. There are no mountain ranges here to break up a line of storms, no coastlines to cool the air and rob it of moisture, nothing but hundreds of uninterrupted miles of open, sun-baked farmland, pumping warm, humid air into the atmosphere all day, giving a bow echo an enormous, unobstructed runway to accelerate along, without ever hitting a geographic wall that might slow it down. Picture the difference between a marble rolling down a smooth, straight bowling lane and one dropped into a rock garden. The Great Plains and the Ohio Valley are the bowling lane. Nearly every part of the world with major mountain ranges or fragmented coastlines is the rock garden. That doesn't mean derechos are confined to summer or to that single belt. A second, quieter pattern lives in the cooler months, when a different flavor of the same storm sweeps through the Gulf Coast states and up into the Tennessee and Ohio valleys, riding along strong, upper-level jet streams rather than summer heat and humidity.
These cool-season derechos tend to be less frequent, but can be just as destructive, arriving in winter or early spring when residents are watching for ice storms and cold fronts, not thinking for a moment about hurricane-force straight-line wind. Across the full year, researchers studying the modern record count somewhere in the range of 20 to 30 distinct derecho events crossing the United States, though the count varies depending on exactly which definition and data set a given study applies. A reminder that even now, this storm type resists being pinned down with the same tidy statistical confidence meteorologists have built around hurricanes and tornadoes. What all of that climatology adds up to is this: the storm that hit Cedar Rapids wasn't some once-in-a-generation freak event dropped onto an unlucky city by chance. It was a nearly textbook example of exactly the kind of storm that corridor of the country has always been geographically primed to produce. Except that this particular one, when the final numbers came in, would turn out to be the most expensive thunderstorm event ever recorded on American soil. And the sheer size of that number deserves to be seen in full before we go any further. $11.25 billion. That is the figure the National Oceanic and Atmospheric Administration ultimately attached to the August 10, 2020 derecho, once insurance claims, crop losses, and infrastructure repairs had all been tallied. A number that placed it, at the time, among the costliest weather disasters of that entire year in the United States, standing shoulder to shoulder in the ledger books with major hurricanes that made national headlines for a week straight. This storm made almost none of those headlines. Not in the moment, not with anything close to proportional coverage. And yet, on a balance sheet, it outcosted most of the hurricanes most Americans could actually name from that same year. And a huge share of that $11 billion figure didn't come from roofs, power lines, or shattered windows at all. It came from something most of the storm coverage never thought to point a camera at: the fields themselves. A huge share of that cost came from something easy to overlook if you've never stood in the middle of an Iowa cornfield in August: the crops themselves. The storm tore through the state at the exact point in the growing season when corn stalks stand at their tallest and most vulnerable, heavy with developing ears, utterly unable to bend far enough to survive sustained hurricane-force gusts. Estimates from Iowa's own agriculture officials found the derecho damaged somewhere in the range of 10 million acres of corn and soybeans across the state, an area larger than the entire state of Maryland, flattened or badly damaged in a single afternoon. Farmers who drove out to check their fields the next morning described corn lying down in uniform rows, pressed flat against the earth as if some impossibly wide machine had rolled directly over the top of it. Stalk after stalk pointed the same direction, because, of course, in a sense, that's exactly what had happened. The same straight-line wind that had stripped Cedar Rapids of 2/3 of its tree canopy, simply continuing its work across open farmland with nothing to slow it down. Insurance adjusters who arrived in the following weeks described a workload unlike anything the region's property claims process had ever handled outside of a major hurricane landfall. Thousands of roofs across dozens of towns needing simultaneous repair, a shortage of contractors and materials stretching recovery timelines out for months. Some homeowners waiting the better part of a year before a crew could even get to their street. Grain storage structures, the tall steel bins that dot the landscape across the Midwest, holding a farm's entire harvest, proved especially vulnerable. Dozens of them across the state were crumpled or torn open entirely, some estimates putting total grain storage losses across the region at tens of millions of bushels, right as the fall harvest was approaching and farmers desperately needed somewhere to put it.
It is one of the strange cruelties of this storm type that its damage compounds in ways a tornado's narrow, well-mapped path rarely does. Because the destruction is so wide and so uniform, there's no adjacent, undamaged town to borrow spare capacity, spare contractors, spare grain bins from. The entire regional support system that would normally absorb a localized disaster had itself been hit at the same moment, across the same afternoon, everywhere at once. That collapse of the whole regional safety net is also what makes this storm's true scale so hard to grasp from any single dollar figure, until you set it next to the one measurement that finally puts it in the same room as the hurricanes it never got compared to on the evening news. And this is the number that puts the entire event into its sharpest possible perspective, the one meteorologists keep coming back to when they try to explain why this storm deserves to be remembered far more prominently than it currently is. Measured purely by the width of the path of hurricane-force wind it produced on the ground, the August 10, 2020 derecho generated a wind swath comparable to some of the strongest landfalling hurricanes in modern American history. And it did so over a landlocked stretch of the country that had never once been asked to think about hurricane preparedness, because hurricanes, by definition, aren't supposed to reach that far inland with that kind of strength intact. A storm system born over the cold, dry plains of South Dakota, nowhere near a drop of ocean water, had somehow assembled itself into something that behaved, for the better part of an hour over Cedar Rapids, almost exactly like a hurricane making landfall. Minus the name, minus the days of warning, minus the category number scrolling across the bottom of every television screen in the country. That gap between the storm's true destructive power and the public's awareness of it going in didn't close on August 10, 2020. If anything, it's still open, right now, in a way that connects this one Iowa disaster to a much bigger question meteorologists have started asking with real urgency in just the past few years. A question about whether the very atmosphere that builds these storms is changing underneath our feet. Whether the corridor Johns and Hurt mapped out in 1987 is quietly widening, intensifying, or shifting into places that have never had to reckon with a storm like this before. And whether the tools meant to catch the next one in time are catching up fast enough to matter. That question about a changing atmosphere doesn't have a tidy answer yet, and any honest account of this storm has to sit inside that uncertainty rather than paper over it. Climate scientists studying severe convective storms, the broad category that includes derechos, tornadoes, and the supercells that spawn them, will tell you plainly that this is one of the hardest corners of climate science to pin down with confidence, and the reasons why matter before anyone hands you a simple answer. The core problem, laid out as plainly as the science currently allows, comes down to this. A warming atmosphere holds more moisture. That part is settled physics, verified in 1,000 different measurements, roughly 7% more water vapor for every degree Celsius of warming. More moisture in the air means more fuel available for thunderstorms, more latent heat available to be released when that moisture condenses, more potential energy sitting in the atmosphere on any given summer afternoon across the Corn Belt. That ingredient on its own points toward a future with more fuel for storms like the one that hit Cedar Rapids. But a derecho doesn't run on fuel alone. It also depends on that second ingredient we talked about earlier, wind shear. The layered winds blowing in different directions at different heights that let a line of storms organize into a self-sustaining engine, rather than collapsing into disorganized showers. And here's where the picture gets genuinely murky. Some of the same warming that increases moisture and instability tends to weaken the temperature contrast between the pole and the equator that drives a lot of that shear, particularly in the cooler months. Researchers studying this exact tension have described it as something close to a tug-of-war between two ingredients moving in opposite directions, and nobody currently knows with confidence which one wins, or in which regions, or by how much. Picture two dials on an old radio, one controlling volume and the other controlling tuning, and imagine that turning the volume dial up sometimes also nudges the tuning dial in a direction you didn't ask for. That's roughly the situation atmospheric scientists face when they try to project the future of derechos specifically. Some research pointing at rising instability suggests we may see more of the raw ingredients needed for these storms, particularly earlier in the season and farther north than the traditional derecho corridor mapped out back in 1987. Other analysis focused on shifting shear patterns suggests the opposite could be true in parts of the year, or that the frequency of the exact ingredient combination might not change much at all, even as individual ingredients shift. Both conclusions are defensible from the data currently available. Neither one is the final word.
What researchers are more confident about, and what should catch your attention hardest,
Isn't frequency at all, it's intensity, and where the danger is spreading. Attribution studies looking specifically at the most extreme, high-end, severe thunderstorm events across North America have found signals consistent with an increase in the odds of the most intense outbreaks, even in years when the total number of storm days doesn't change much. In plain terms, the same number of derechos each summer might, on average, be pulling from a slightly hotter, slightly more moisture-loaded atmosphere than they were pulling from 30 years ago. And a storm engine fed richer fuel doesn't necessarily fire more often, but when it does fire, it has more room to run harder before it burns out.
there is also a documented pattern, still being actively studied, of the traditional warm season for severe convective storms, stretching earlier into spring and later into autumn, across parts of the central United States, which matters enormously for a very practical reason we'll come back to. A derecho arriving in April or October catches a population that is mentally filed severe summer weather away for the season, exactly the kind of psychological blind spot that turns a survivable storm into a deadly one. There's one more twist inside this climate picture that deserves its own moment, because it runs against the intuition most people bring to a warming world. You might expect a hotter, wetter atmosphere to simply mean more storms of every kind, uniformly, everywhere. Instead, some of the most careful recent modeling work on severe convective storms across North America suggests the changes may be uneven and, in places, almost paradoxical. Certain subregions could see the environment become slightly less favorable for the specific ingredient combination a derecho needs, even as the same broad warming trend makes other categories of extreme weather nearby, like flash flooding or extreme heat, unambiguously worse. That unevenness is exactly why serious researchers resist the kind of tidy, one-line answer a headline wants. And it's also exactly why the agencies responsible for actually warning the public about these storms have had to start building their entire approach around a different strategy altogether, one that doesn't wait for climate science to settle the long-term question before doing something about the storm that might be forming next week. That shift in strategy is happening right now, inside the same building in Norman, Oklahoma, where that slight risk outlook was issued at midnight on August 10th, 2020. And what forecasters have actually changed since then goes further than most people would expect. The Storm Prediction Center didn't wait for a perfect derecho warning product to materialize out of thin air after the Iowa disaster. What it did instead was lean harder into a tool most of the public has never heard of, the mesoscale discussion, a plain English forecast document written specifically to bridge the gap between the broad, hours ahead outlook categories like slight or enhanced, and the narrow, minutes ahead warnings issued once a storm is already bearing down on a specific town. These discussions are written by human forecasters in real time, often flagging the exact kind of atmospheric setup that produces a derecho. Strong instability paired with organized wind shear along a well-defined boundary, sometimes hours before the first bow echo even appears on radar. On the morning of August 10th, 2020, in fact, that unscheduled 8 a.m. bulletin we mentioned earlier was exactly this kind of product. Forecasters recognizing the ingredients assembling over Nebraska and pushing an urgent update out the door well ahead of the normal schedule,
buying emergency managers and local meteorologists in Iowa a few extra crucial hours to start sounding alarms before the wind ever arrived. Radar technology itself has also quietly improved in ways specifically relevant to catching this storm type earlier. Dual polarization radar, which became fully operational across the national network in the years leading up to 2020, doesn't just measure how fast air is moving toward or away from the radar dish. It measures the shape and orientation of the raindrops and hailstones themselves, which turns out to be enormously useful for spotting the telltale signatures of a strengthening rear-inflow jet before it fully punches through to the surface. Forecasters trained on this newer data can, in some cases, see a bow echo's engine beginning to spin up in the mid-levels of the atmosphere before the worst winds ever reach the ground, shaving precious extra minutes off the warning gap that cost so many people in Cedar Rapids any real chance to prepare. There's a deeper structural fight happening too, one that goes beyond radar hardware and into the language of the warnings themselves. In the years since 2020, there has been a growing, serious push within the meteorological community to give this storm type its own dedicated public alert, something that would appear on a phone as clearly distinct from an ordinary severe thunderstorm warning as a hurricane warning is distinct from a small craft advisory. Some weather service offices have begun experimenting with more forceful, plain language phrasing inside severe thunderstorm warnings themselves, phrases borrowed deliberately from tornado warning language, describing life-threatening, widespread structural damage and extremely dangerous situation wind events, an attempt to inject urgency into a warning category that has, for decades, carried a kind of built-in shrug for anyone who has ever safely sat through a routine summer squall. Whether that experiment eventually produces a fully separate derecho warning, complete with its own name and its own siren tone, remains an open question the agency is actively wrestling with. But the pressure to solve it has only grown since a city the size of Cedar Rapids discovered, in real time, exactly how little that shared warning language actually communicated about what was coming. None of that technical progress, though, changes one blunt and uncomfortable fact sitting underneath the entire modern warning system, a fact that has almost nothing to do with radar or wording and everything to do with human psychology. And it's the exact thing your phone is quietly failing to tell you every single time an alert like this one goes off. That gap between what your phone tells you and what a trained meteorologist watching the same radar loop already knows is exactly why local knowledge and old-fashioned situational awareness still matter enormously, even in an age of instant digital alerts. Meteorologists at weather service offices across the derecho corridor will tell you, almost universally, that the residents who fared best on August 10, 2020, weren't the ones who happened to glance at their phone at the right moment. They were the ones who noticed the sky itself behaving strangely. A wall of dark, almost greenish cloud advancing with unusual speed and uniformity along the horizon, and made the decision to get inside and away from windows before any alert told them to. That's an uncomfortable thing to admit about a supposedly high-tech warning system in the 21st century, but it's borne out repeatedly in post-storm surveys. The sky, read correctly, is still often a faster and more informative messenger than the device in your hand. There is a practical takeaway buried inside that discomfort, though, and it's worth stating plainly, rather than leaving it as an abstract worry. If you live anywhere within that broad corridor running from the eastern Dakotas through the Ohio Valley, and you see a long, unbroken line of dark cloud on the horizon, moving with obvious speed on a hot, humid summer day, particularly one where the morning forecast has already mentioned words like enhanced risk or widespread damaging wind, treat that sky the way you would treat a tornado siren, not the way you'd treat an ordinary afternoon shower. Get away from windows. Get to the lowest, most interior part of a sturdy building. Secure or bring inside anything in a yard that wind could turn into a projectile. And do all of that before checking whether an official warning has actually been issued for your specific address. Because by the time that warning arrives, in a storm moving at highway speed across hundreds of miles, the leading edge may already be less than 15 minutes away, sometimes less than that. This is not a call to panic every time clouds gather over the Midwest in summer. It is a call to recognize one specific, describable sky
and to trust it. And that brings us back, in a way, to the exact spot where this story started. A modest cluster of thunderstorms over South Dakota that nobody outside a forecasting office was watching closely, on a morning that began, by every official measure, as unremarkable.
Because this is the truth. This entire storm forces you to sit with. And it's the truth every meteorologist in that derecho corridor carries with them every single summer, whether the public is paying attention or not. Somewhere across that stretch of America right now, on some ordinary weekday morning that looks exactly like every other, the same ingredients are quietly assembling themselves again. Warm, humid air pooling over open farmland, a jet of wind aloft, blowing at just the right angle across a slower layer near the surface, a boundary sitting somewhere over the plains, waiting for a trigger. Most days, those ingredients never fully align, and the afternoon produces nothing more than a pleasant thunderstorm and a rainbow. But some days, they do align, completely and without warning, to anyone standing on the ground, looking up at what still looks, for now, like a perfectly ordinary sky. The line is always somewhere out there, forming or dissolving, gathering strength or losing it. Invisible to satellites, in the way a hurricane never is. Unnamed by any agency in the way a tropical storm never is. Waiting for the one morning when every ingredient locks into place at once. Cedar Rapids didn't get unlucky in some freak, unrepeatable way on August 10th, 2020. It got exactly the storm its geography has always been capable of producing. The same storm Gustavus Hinrichs was trying to name back in 1888 when he stood in a field of trees, all fallen the same direction, and realized the word tornado simply didn't fit what he was looking at. The wind that flattened Cedar Rapids didn't spiral, didn't announce itself with a name on a hurricane tracker, didn't give anyone the courtesy of a slow, visible approach across open water. It simply arrived, in a straight line, exactly as its name always promised it would, and somewhere over that same wide, unbroken stretch of American sky, on some future morning that will look, right up until it doesn't, entirely unremarkable, it will arrive again.